Good morning. My name is Harsh Richaran and my roll number is 5D1. Today, my topic is Principle of Inclusion and Exclusion on Partial Order Sets. Introduction. We first briefly mention the background and progress which lead to the main theorem in this paper, that is the principle of inclusion and exclusion on partially ordered set. In the process of wrestling with the enumeration problem on irreducible machines, for which a series of enumeration theorem under group action cannot answer. The principle of inclusion and exclusion on partial similarity was discovered furthermore by the motive similarities were discovered. Residues or types of finite systems such as mapping and finite machines, a cardinal conjugation relation on the set of chains in a partition lattice was introduced by the permutations on the chains. An invariant of each cardinal pre- preserving type functions from a partial lattice to partition posets of an integer and a vector, and a cardinality of each class was represented by the closed formula on the invariants. Subsequently, the concept of reducible or irreducible mapping systems relative to a reduction domain was established, and then they equals correspondence between mapping system and on the other hand the inclusion and exclusion on partial seminar was abstractly extended on similarities by introducing a weak morphism from a similarities into the power set of object. We have given the three different proofs of the theorem 1 into 11, in which the Rhodes theorem, theorem 1 of 17, plays an important role, that is the closure relation on the power set of a semilattice is used, and the other 12, 15 are elementary in an application of the theorem for a given semilattice and a map from a semilattice to power set of an object. It is of interest whether the map is a weak morphism or not. Then further application of the theorem to Boolean similarities product, partition similarities and rooted trees were shown. Theorem 2 of 11, proposition 3 of 12. Also the theorem was restarted in terms of valuation and distributive lattice instead of measure on the power set of objects. Theorem: let Om be a non-empty set and P be the finite partial ordered set with a unique maximal element. Let F is to P be weak morphism on P. Then of any measure M on P, the following identity holds. Mu, where C is the set of all chains in P and L into C denotes the length of chain C. You can see the formula for you can see the theorem in this slide. two different proofs are given. Let P be a finite poset with a unique maximal element and L be a finite semilattice. The first proof is carried out by an extension of the closure relation on P into L in the proof of theorem 1 of 11 to a closure relation on P into P. The second proof is elementary without the use of the closure relation, in which P into P is classified by the preordered incomparable pair contained in each subset of P and a bijunction on the set of non-chains in P is defined. Let F is equal to P be a weak morphism on P. Note that there can be more than one minimal upper bound z of x into y satisfying. Then we define an algebraic system as follows. For each x and y in P, we choose a minimal upper bound z of x into y satisfying and denote it by x or P. When P is equal to x, comma y, this algebraic system is called quasi-semilattice, included by F. Note that the operation is demorphic and commutative but not necessarily associative. Also note that for a weak morphism F, there can be more than one quasi-semilattice included by F. It follows immediately that x is less or equal to y in P and there x comma y is called x or y. If there exists a unique minimal upper bound x comma y, the join x or y for each x is a P denoted the set of all incompatible pairs. Remark 1. The theorem can be dualized, which result in order 3 cases, that is or and are interchangeable by setting f of x or f of y or f of z. For f of x or f of y or f of z, and for any finite poset with a unique minimal each element, the theorem holds. Remark 2. Let D comma or comma and B distributive lattice and A comma plus B commutative ring with identity a map satisfying u x and y plus u x or y is equal to v into x plus v into y. For each x and y in D is called valuation on D. Then it is easily shown that the theorem can be restarted in terms of valuation on distributive lattice instead of measured on P into P. Remark 3. In an application of the theorem for a given poset P and a map F is to P gives, it is of interest whether F is a weak morphism on P or not. Let P be a finite chain, then a map F is to P gives P is always a weak morphism on P and P is equal to C. Thus, the incursion and excursion principle is derived. Let P be a finite semilattice, then a map satisfying for each x and y in P in a weak morphism on P. Thus, the principle of inclusion and exclusion on the semilattice is derived. Thank you for giving this great opportunity to me.